So I have my new 2450 SMU, but to get the most out of it, you need to use triaxial cables to use the driven guard features of the rear terminals. And those triaxial cables can be mighty expensive, and by the time you start buying things to fit on the ends and all that, you can end up spending half the cost of the SMU. So I tried to figure out what kind of system I could make here that would work for my rudimentary purposes and give me some flexibility with the minimal expenditure. So I had one set of the HP low triboelectric noise cables, triaxial cables, that a friend from the EEV blog sent me. And I got another set off of eBay, 3 meter, and thought, well, I'll cut them in half and I'll do a connector system on the end. So what I did was I made a connector setup where I'm using a Tyco socket and pin, standard socket and pin, and I use the pins on whatever I'm connecting on the one end, and I have the sockets built in here, and I have the inner driven guard all the way out to the tip and the outer shield all the way out to the tip, and later on we'll show the construction of those. But my purpose here was to be able to put any combination of things in the end of this that I might desire. So for just standard connector type things, these cables are not very flexible. So you need something on the end that will allow you to bend around and hook onto things without the stressing whatever you're connecting. So these are nice superfine stranded silicone, and Pomona pinchers, which are my favorite, and these just clip on. And the socket, you'll see later how I made these shrouded connectors just using glue-lined heat shrink. So these would take care of just a connection where you're going to use 4-wire setup, whether it's measuring high resistance or low resistance using 4-wire setups. Then also to be able to connect into a banana jack. Well, these still being very stiff, I wanted something where I could not have it stress the jacks on the multimeter. So I put a length of Pomona silicone, superfine stranded silicone wire on here with the jack, so these can flex around and do whatever they want without putting strain on the sockets in the bench meter. So that's what they accomplish. And then there are times when you need to do things in a shielded box, and I just happen to have this really nice little container that's just kind of tailor-made for that. So I made some brass tubes, swaged them down to fit onto the actual size of my over my heat shrink on these, and that allows me to stick these into the box and have some shielding on them. And the cables, as you can see, are marked sense low, force low, force high, and sense high, so you can keep them straight. And in a lot of situations, you only need to have your force lines. You don't need the sense if you're doing some certain current measurements. But typically, you have your force low connected to your box as a just to keep the noise down. The inside of the box I lined with virgin Teflon sheet, and the modeled effect there is what you see is just the I used 3M adhesive. Film adhesive. I put it on the back of the Teflon, even though it doesn't really stick that well. It sticks well enough that if you cut the pieces real nice, that they would stay in there. So that gives us a real high leakage or low leakage situation with the Teflon shielding the box. And then the connectors that I have in here, these obviously have the same plug-on situation where you can just plug into the ends of these. But I wanted a really small connector that got a really good grip. Now these are from Radio Shack, or at least that's where I got these, but they're really worthless. I mean, they don't hold anything worth a darn. Things just fall off of these. But I realized that if I modified them slightly, I could take these and cut a groove in them, shorten them up, and cut a V groove across, so that when it gets a hold of the wire it's got a death grip on there. You're not getting that wire out of there. You're going to rip things off before you can rip it out of the. So that gets a good grip on there, and they're nice and compact. Just use some glue lined heat shrink to dress them up a little bit. And these fit inside the box. By using the same 40 thousandths pin setup on these, that also allows me to use my Kelvin banana jacks and my Kelvin 25 thousandths pins and socket for doing very precise resistance measurements where there's actual Kelvin connections on these. There's a video on my channel making the Kelvin banana jacks that'll show the details of how these are constructed. There's more to them than meets the eye from the outside here. So that lets me get my whole system here where all these things are interchangeable, and just gives me a lot of versatility. So just a little example here looking at diode leakage. I have a 1N4148 in here, and so I'll have a little fun with seeing what's going on. Right now you can see this thing's chugging along here at the bottom, real close to zero. If I go to menu, sheet, and jump to the bottom here, I can see what's going on. You can see we're looking at in the low hundreds of femtoamps of leakage of current that's flowing there. And that is, I accomplished that by using relative mode to zero out the base leakage that's going on. So it's pretty consistent down there. I'm using, we can just go over here and see that I'm using a filter with a repeat of 2. We're on 10 line cycles, 6.5 digit display, and as you know, it's relative out. So this is basically our baseline for 0, which is 0. And we can come up here and see what that looks like. Now, just want to show you some effects of just putting the lid on the box. I just put the lid on the box there, and you can see the spike we get there. Experimented, and it has nothing to do with whether I have a ground strap on, whether I put a ground strap on the lid, whether I ground the case to earth ground or whatever. It's just the charge effect that goes on there. So we can easily just come here and go data, clear, graph, and we can clear up again and get back to where we got rid of those. And we're chugging along here at the bottom, as you can see. Now what I'm going to do is we just get a little baseline there so we can see what's going on. And I'm going to hook up, I have 10 volts on this right now on the output. And I am connecting right now. And you'll see we go up to about 700 picoamps. That's where we are right there. And that's with the 10 volts on there. So this just lets you see if we come off of there with our connector, we will, on one leg, we will drop back down. You'll see that we get a consistent 0. And so we were reading good stuff there. And one thing that you'll notice is I'm going to go back on there, and they always tell you to make sure you're using a shielded box, light shielded box, if nothing else, when you're doing this. So you can see here we're back on our whatever 800 picoamps. Now I'm going to take a flashlight and I'm going to go shine in there right now. And you can see the rise there from going in with the flashlight. And I have experimented with just pulling my hand there and seeing whether just the presence of my hand affected it. But it's definitely the light. I take the light away and we'll see that it'll drop back down. So there's definitely, the effects are definitely there. And what we can do to see that effect better is just go to data, clear, graph, come back here, and this way we'll get a higher resolution view of what's going on for our baseline. You can see here we're at 10 picoamp increments on the side here. So now I'm going to shine the light on, and you can see what's going on there much better. That's with the light shining on it. And that'll settle out. It's probably for me dancing around here with which LED is getting closer to it. Take the light away, and no problem. And I believe I'm just going to hold my hand over this so I don't get any effects of the, and that's just my hand covering the box. You can see the drop just from getting the ambient light away from the diode. So you can see there we dropped about 10 picoamps. And I'll put my hand back and it'll bounce right up again. So it's really interesting, and just having graphing and high resolution is just really educational for what goes on with these things. So now a neat thing you can see here is what I'll do is I will go here and go to menu, and we'll go to a sweep, and we'll do from 0 to, let's say, 20 volts and 0.5 volt increments. Okay, we'll generate the sweep, and we will go home and we'll go to the graph, data, clear, graph. So we're starting from scratch, and this will start, and it's going to do a sweep now, and we're going to get a nice trace of what's going on as it goes through those ranges. So it's actually doing a curve trace right now. So here that trace is complete. You can see up at the, we got to the 20 volts, we were at about 2.5 nanoamps. But down here at the knee, I'm not really sure exactly what's going on there. It looks kind of discontinuous, so let's go see if it really is. So let's interpolate and say, okay, let's do 150 millivolts, and we'll go do another sweep. So we'll set the sweep, set this to 150 millivolts. Steps, let's just do 10 millivolt steps. Generate the sweep. Go home. Here, data, clear, graph, and hit the trigger. Now we'll get a little higher resolution view of what's going on down here at the bottom to see if we got a smooth situation. And we can see that it was just the fact that that first step was in the beginning there. It was just too large of a step to see what's going on. And of course we could zoom in even further, do smaller increments, but just shows the flexibility of being able to dance around with this thing and instantly on screen get some very useful data to see what's happening. And we're done here. We stopped at our 150, and we can see very nicely what's going on. And see that at 20 millivolts, we've got about 300 picoamps of leakage, and we peak out at about maybe 700 picoamps. And as always, you can go see the real data under sheet here, and we can jump down to the bottom. Our last one was 723 picoamps, and this is all available on a USB stick also. So just very, very handy to be able to see what's going on. So all of our pieces fit inside the box for a nice storage place. Put the lid on, and that's my low leakage shielded box. These have the 40 thousandths pins. These are the standard Tyco amp 205089-1 40 thousandths diameter pin, and sockets are 205090-1 sockets, and these make a real nice connection, quick connection for being able to plug things in like this. This is the HP low noise triaxial cable. Has the outer insulation, has tinned conductors for the outer shield, has some type of fluorocarbon insulation between the outer shield and the inner shield. The inner shield is silver plated copper wire. Then this inner insulator is actually a two-layer deal. This is very slippery, this black stuff on the outside. It's a fairly thick layer on there, and I think that's part of the low noise aspect of it, is the very low friction situation between this silver coated copper. And then the inner strands, or 7 strands here in the center, are the center conductor. So the important part here is in my connection to get this outer or the inner shield, the driven guard, to be cover all the way out over top of the actual connector, and also have the outer shield to the shield ambient noise also up as far as possible. First step is to measure the dimensions of this cable, the outside diameter, what it is over the wires when they're constrained nicely by the outer insulation, diameter of the next step of insulation, diameter over the inner shield wires, diameter over the inner conductor, and then the final conductor, so that this can be modeled in SolidWorks so that we can determine how we're going to design this thing.
Here's the Triax cable. This is the PVC outer shield, outer insulation. This is the outer shield wire there in the gray. This is the intermediate insulation, the inner guard shield, the driven guard shield wiring there. This is the inner insulator, and then the inner conductor. This is where we're going to reduce the diameter of that insulator so that the heat shrink will pass over that. Now turn on the actual socket so you can see the socket in place. There's where the actual pin will come into the socket. This is where it is soldered onto the inner conductor. This is why we needed that bushing to hold the connector concentric with the insulation so that this would be centralized and then guide that hollow counterbore cutter to do this relief. Whole purpose of that was to have the heat shrink go over this joint so that we don't have leakage through this small gap. Then we put the heat shrink over top here, and we can see that heat shrink is now insulating this inner conductor. Now we'll turn on the copper sleeve, and the copper sleeve, as we can see here, is connecting the intermediate guard. The actual guard wiring is connecting to this. So what this is doing is maintaining the guard all the way out over the connector with this insulation so that we have the effect of the guard all the way out to the tip. Then we have our actual tip that we've made out of the black Delrin, and this has a little guide to guide the pin in and to prevent the ability to short between the actual force and the guard, because we don't want to short between those two. And this also insulates all the way back to this insulation. And then the next copper sleeve right there actually bridges across and gets to the outer shield wires, and so that carries this outer shield all the way out to the end here. And that all of these, the coppers, were actually crimped with using collet and lathe so that they're actually forcibly connecting to the wires very firmly and actually sandwiching everything tight. They're not just a slip fit on there once they're crimped. And then the outer heat shrink goes on and just forms the protection over the outer shield up to the insulation. And that's the whole design.
So here's a drawing I threw together just to be able to make the pieces. Got my dimensioned section of the low noise cable. I've got my heat shrink cut. I've got the outer piece. It says PEEK, but I end up making out of black Delrin. There's the actual connector. This is the copper pieces are turned right there, and this one has a little flare on the end so that it can actually get up over the braided shielding, not braided but stranded shielding. And over here's one that I almost forgot. Because this the way we designed this, we want the insulation to overlap on this. This actually has to get the inner conductor. This needs to be concentric. So I have this piece here which will slip over the outer conductor here like that, so that when I solder this, I will be able to have this be concentric. Then once that's done and that concentric pieces, the pieces actually soldered on. Then I made a tool here, which is just a piece of tool steel, and I just hand ground basically like a counterbore, and that will actually just slide over this after this is done. It will slide over this piece as a guide. Like this. This will be soldered and concentric. It's not cooperating, of course. Get this on here. This will actually be soldered and it'll actually butt up tight. Then this will come on, and this will actually machine this down to a diameter so that when I put the heat shrink on over top of this, this will actually bridge the joint. We won't have a place where there's an actual open joint here. The heat shrink will come over this, over top of that, and be the same diameter. So that's what this piece that we made here was for. It wasn't, I didn't actually draw it in SolidWorks, but that piece is to get this soldered on concentric, because the hole is much bigger in this. The solder hole is much bigger than this conductor, so you can just flop all over the place. Another thing that's very important with these Triax cables, when you're trying to work with very low currents, is leakage situations. So contamination, fingerprints, all that's important. So as I machine all these pieces, the copper and all that, in order to keep it from oxidizing, I just throw everything in isopropyl alcohol, and basically keeps the air away from it and keeps it degreased. And take these out and carefully blow them off using gloves, so that I don't get any handprints or anything on these to contaminate any of this. One of the things I found was a little trickier than I anticipated was cutting this without mauling the shield wires, without nicking the insulators, and especially this one, getting down into this one and cutting this without nicking these, and having that be a bad situation was very difficult. This inner stuff is pretty hard. It's not like real soft Teflon. It's pretty darn tough. So without some kind of controlled depth cutter, I just was not having much luck. So I was trying to think of something. I did order one of those inexpensive coaxial cable cutters that's supposed to have an adjustable depth, but it's not here yet. Here's the tool I was talking about that I ordered. It has the adjustable blade here where you can actually set the depth that goes down in there, but of course you're not able to set it to an exact value. So in the grand scheme of things, I actually like the caliper version, but this will come in handy anyhow. So I was thinking around what I could do, and caliper is always a good starting place for something where you want adjustable depths and things like that, because it's got a zeroable graduated divisions. So I thought, you know what? Looking for a razor blade here. A razor blade actually fits in this recess of this caliper as it's made. So I can sit here on this shoulder, and I took a regular razor blade, peeled off the outer cap, cut it in half with a Dremel cut-off disc, and then just held it in here, and then held a block on the top here to hold it parallel, and then just wick some wicking super glue in the joint here, so that glued it in place. It's sitting here, actually. The glue is just holding it in place so it doesn't move. The actual cutting pressure is here. And then I just made that flush against the hardened block and then zeroed it, so now this reads directly in the amount of blade protruding. And I can set it to these, and on my sheet I calculated all these radial one side depths, 28.5 to get through this, down to get through both of them we're looking at 0.35, and as we walk our way down through, we have all the depths we need to get down through and cut this. And I just have this clamped in the pan of ice here on my weighted base on the table, and then I can just simply hold the insulation or whatever diameter I'm referencing from, hold it down tight on here and just roll it right over this and get a nice controlled depth of cut. And it cuts nicely. I can actually control cut through right through the shield wires, which are about 7 thousandths diameter. So I can do all the cuts I need to do precisely just by setting the correct depth on here and locking the position and rolling them across. I'm all for 3D printing and all the variations of it. Extremely neat technology, doing some amazing things in mold making and things like that. But this is an example of something where 3D printing isn't for a long time going to be able to do something that just a plain old lathe could do. You could buy a lathe that you'd be able to make these parts on for way less than the generic low-end 3D printers now. Here's the solder bushing I was talking about. You can see the hole is still there, the solder hole. I'll be able to wick the solder in, and this is holding the socket concentric with the this inner black inner insulator. Here's the socket soldered to the inner wire and with the inner insulator trimmed with that heat shrink over that, so the heat shrink is straddling the insulation over the inner insulator so that there's no gap there for the where we're not insulated completely. Copper sleeve slid over the heat shrink, and that'll get crimped in the lathe to actually seat down on that tightly. Here the first copper sleeve is on that is carrying the inner shield out, all completely out over the connector. Here's the insulator. This is the other insulator that's going to go on top now, that's going to slide over top of this and slide all the way down and come up like this to bridge that. Here's the final outer sleeve that contacts the outermost shield. This slides on, slides completely over, rides over top of that, and that gets crimped like that. So here it is with the final layer of heat shrink over the outside. That's just covering the outer shield, which is chassis ground of the SMU.
I'm using a hardened pin here that's just lubricated with some grease to spin a flare flange on there to get better solder engagement with the case.
Here's my nice tin for my shielding box. I've got my holes that I punched in using the $40 hole punch. These things are pretty handy. Drilling a hole through the material this thin would have been a nightmare and a mess. And then here are the brass pieces that I just made out of some general hobby tubing, and with the flare that you saw me put on there in the lathe. The crimped down end is done with a collet, just crunching it down to a smaller size, and then the flare is just done with the hardened pin with a little grease and hand spun on the end. Now I'll solder those in. Cutting the heat shrink to length here with my digital cutter. So I had an idea when I was putting the heat shrink on these. I thought, oh, if I make a Teflon version of this tip right here, I can put the heat shrink on, the glue lined heat shrink, let it cure on here, cool it, and then spin it off and it'll form a shroud. So that's exactly what I'm going to do right here. I have my piece, I have my heat shrink I'm going to stick on here as a start, put my pin all the way down in, grab my gun that you can hear in the background here, and shrink this up. This is 3:1 reduction shrink ratio heat shrink. And then I will push it down, make sure it's pushed all the way down to the shoulder here, and I'll go over in the sink and I'll cool this. I'll be right back. So after going over to the sink and cooling this off real well, you can grab this and just give it a firm twist and break loose the glue line part from the Teflon. If you don't cool it off real well, the glue actually gets about half a bite on the Teflon, but once it's cooled off completely, chilled, it'll pop right off. And there you've got a socket formed that fits this exactly and gives a little protection since this can get up to 200 volts.
I hope you found something useful or informative in this, and if so, please give it a thumbs up.